You've got to focus more acutely, especially if you're running up here in the Flatirons, which is particularly jagged and rocky. You've really got to pay attention to what you're doing. I spend most of my time thinking about my foot placement and where the next foot's going to go. And the more complicated, the better in my mind, because, you know, it draws you out of whatever you were involved with before. There's certainly some pretty distinct parallels between the preparation required for running up here and the preparation that's required for putting a rover on the moon. The approach needs to be similar in that the risk of failure needs to be extremely low. It requires that you take a moment to step back and really analyze what you have to do to make sure that you ensure that that's the case. And so it's doing the research and the due diligence, even in the face of a lot of incentives to skip it. And then when you're putting a rover on the moon, that requires that you and everybody on your engineering team have the discipline to take a step back and evaluate what needs to be done before proceeding forward.
All right, perfect. You guys ready?
Yeah.
We're just gonna go so we can open it up, show you guys how fast basically astronauts are gonna be traveling on the lunar surface. All right, ready? Here at Lunar Outpost, we make mobility and robotic systems to enable a sustainable presence in space. You're moving pretty quick, and like you are going to be catching a little bit of air at this speed. So for the most part, astronauts are actually going to be traveling a little bit slower than this. Small robotic rovers to start, all the way up to large space trucks that are going to build the infrastructure of space. So everything from your power, your communications, your habitats, roads, launch and landing pads, and everything else. We are the workforce that makes that possible. Lunar Outpost, it came from me growing up around the space industry. So I actually grew up right outside of Johnson Space Center. And so having that always in the back of my mind, me wanting to be in the space industry, was a huge motivator for me. Right now, Lunar Outpost is an industry leader in mobility and robotic systems. So we are going to successfully operate a rover on the moon. It is a point of pride, it's a point of excitement, and it's something that I think brings a very good value into the culture of Lunar Outpost.
The moon is something quite unique. It is something that everybody and every culture and every language group and every country has some kind of relationship with. It is the only place that we have all seen. Everybody on Earth who is able to has seen the moon. The moon is a continent with a surface area the size of Africa. And we've explored a street somewhere in a peculiar little town that's not like anywhere else we've been to. So we've really just scratched the surface. The 1960s was an extraordinary era for space exploration. There was really this drive, and a huge amount of resources were devoted internationally to getting to the moon. Can we do it? Can we do it first? Can we do it the biggest? To showing that it could be done. So we know that this can be done. And then there was a hiatus, like many years, when the moon wasn't really the focus of what we were doing anymore. What we have seen in recent years is a resurgence of interest in the moon. Different countries, different actors from around the world wanting to go to the moon. What we're going to need to do, especially as our landers get bigger, is to create surfaces that they can land on which are safe. There was a recent landing which had a fantastic video associated with it of the Firefly lander throwing out material from the surface. So landing pads, for example, are going to be very, very important. Or we're going to need roads, we're going to need infrastructure on the lunar surface, and creating those things is going to require mobility.
For those that are interested in doing extreme sports, like you find out here in Colorado, the correlation for your career is, in either case, I think it's just a desire to kind of take it to the next level.
Our first mission is Lunar Voyage 1 with our MAPP Rover, the mobile autonomous prospecting platform. So MAPP is a sub 20 kilogram class rover, so it's probably, yay big.
Mobility on the surface of the moon can have many different forms. So in the 1960s, we saw astronauts sitting in a vehicle that they were driving around on the lunar surface. This is really a massive enabler in those later Apollo missions compared with the early missions where we just had crew walking around on the surface. And so one example of mobility would be a human carrying vehicle where astronauts can sit in it and drive around. This allows them to access places they would never be able to get to otherwise. But we also do a lot with robots, and increasingly we rely on robots. So robotic vehicles can be very large, but we can also have much, much smaller rovers, those things the size of a shoebox. And those shoebox-sized rovers, they're very limited in what they can do. But if you have a very specific problem, a very specific task for them to do, that could be deploying an instrument or accessing a very particular place in a very short space of time or demonstrating a technology, though even those very, very small shoebox-sized rovers can be super interesting and can be very useful too.
Rovers are step one. We have to show that it's possible to go to the moon and drive around on the moon successfully as a small commercial company.
The MAPP platform itself has had numerous iterations as we've developed as a company. Our first one, MAPP 1.0, was a small rover really to test this concept primarily from a mobility perspective. MAPP 2.0, we really upgraded with additional cameras and autonomy features. And then MAPP 3.0 evolved a lot by adding additional sensors. That rover has 2 stereo camera sensors. It has a wheel cam, it has a thermal cam, backup nav camera. For Lunar Voyage 2, that rover has a LiDAR. So we've increased its capability for sensing, increased its compute capability for autonomous functions, optimized the wheels to mitigate dust, and fine-tuned the thermal environment to survive the South Pole. 3.0 is really the version of the MAPP rover that we're flying on our Lunar Voyage missions.
It's a mobility platform that could go anywhere on the moon.
In the immediate term, rovers really provide a ton of value to those kind of research and testing opportunities or areas of interest in private payloads and also research organizations that are trying to use their instruments to understand more about the lunar surface or do specific science investigation.
The sun could set at equatorial locations for over 14 Earth days. Down at the South Pole, it looks like we should be able to kind of play Frogger with the sunlight and have dark periods no greater than 150 hours of night. But as we expand our range and try to go farther north, then those nights become longer and longer. And there's a lot of heat transfer that's radiating out into the darkness of space.
Everything we build, if it's touching something else, we have to manually put in a contactor that says either this is the resistance or these are the material properties of.
In the short term, I do think there's a really large opportunity for our rovers to help facilitate the understanding of the lunar surface.
In the last few years, we've seen very real demonstrations of how challenging it is to land on the moon. It's challenging for anything to land on the moon. It's more challenging to get a rover down and operating there. The major space programs of the world, primarily NASA and the Soviet Union back in the day, and now China, got pretty good at it. They learned how to land things on the moon with these big government programs, big expensive government programs, and had a pretty high success rate. Now that private industry is entering the picture, we're once again seeing how hard it is. It's interesting that all this learning we did over the decades from the 60s forward kind of reversed itself. And there's a bunch of reasons for that, but primary among them is it's just really hard to do. It's tough to get any amount of mass down to a planetary or lunar surface without crashing or without going too fast sideways and skidding to a halt, tipping over. if you're tipped over, it's really hard to deploy a rover out of a lander. Even if a lander lands properly, it's really challenging to get ramps down, drive the rover off, and get going and keep going.
The moon is an anchor point for understanding the whole of solar system history, to understanding how planets are formed and evolved, to understanding the history of our own planet. Around the epoch when life was emerging, there are things that the moon can tell us and records about the history of our own planet that have been lost from our geological record. And so the moon is a tremendous scientific opportunity. But then in recent years, we started to have missions in orbit. And what we saw was the samples that we have from Apollo, the samples that created the basis of our entire understanding of the history of the Earth-Moon system and how planets are formed and created, all those samples come from a place which is unrepresentative of the moon. It's really very unique and quite special and quite weird. So if you want to understand the moon, what we've learned is we need to go back there. We need to go get samples from all over the place.
So to really understand the importance of mobility on the moon, did you get in a car today? Did you ride a train? Did you take some form of transportation? And 99% of people that are doing anything, the answer is going to be yes, right? You cannot have a functioning society and civilization without mobility. It's the backbone of all activity.
What robots can do very well now is land and drive around, do a little bit of sampling and exploration. In the future, they'll be able to grab samples from more than just a lander location, bring them back and return them to Earth, which is handy if there's specific things you want, like far side or South Pole, which we haven't sent humans to yet. So like any robotic probe, whether it's a rover or an orbiter or a simple flyby mission, these machines always go to the dark and scary places first.
For Lunar Voyage 1, landing sites we're looking at are all potential future Artemis base camp sites. So these are the sites not only astronauts are going to be going, but potentially where they're actually going to drop a habitat on the moon, which is pretty awesome. We get to scout out the Lunar South Pole for astronauts that are going to be going here in a few years.
The South Pole of the moon is considered, I think, generally more scientifically interesting because there are places on peaks where the sun almost never sets. But also we have craters that never see sunlight. And these places we know contain water ice and other chemistry that's been trapped in the cold there. So there's a potential resource available to us, water, which is hydrogen and oxygen. So water is useful, hydrogen and oxygen are also rocket fuel. So we could find areas where we have near continuous solar power next to areas where we have a deposit of rocket fuel.
Right now, we're here in the desert of North Los Angeles County. It's very hot, dusty, windy, the perfect conditions for an extreme environment test for our airplane. So I started my career actually working for Boeing Space Communications, working on the development of cryogenic launch vehicle propulsion systems for the space shuttle. I moved to NASA's Jet Propulsion Laboratory, working on the development of electric propulsion systems for deep space exploration. After that, I worked on the development of Mars entry, descent, and landing systems, and worked on the team that landed the Curiosity rover on the surface of Mars, and then finally moved over to working on a payload for the International Space Station. Hydrogen as a fuel has been the workhorse of the space program. That's because it has so much energy per unit mass. It's got about 3 times the energy per unit mass as traditional hydrocarbon fuel like diesel or Jet A or avgas. You get a much bigger bang for the buck, or bang for the pound, or bang for the kilogram.
Going to space has driven amazing technological advancements, but it's brought them back down here to Earth, and everything from our cell phones to the microchips you use every day to GPS to material science, all of that comes from the space industry.
The first use of integrated circuits was in the Apollo spacecraft. The first use of flyable advanced computers was in the Apollo spacecraft. Metallurgy engineering that took place for the Saturn V took us light years ahead of where we were. So there's all these advancements that generally don't happen unless there's a push and a forcing function, and spaceflight's about the toughest forcing function there is. So when you can master that, you can do anything.
My goal as an engineer, as a professional, as a business owner, and as a commercial pilot is to decarbonize aviation. You can do that by changing your fuel source, also switching from traditional internal combustion engines over to electric propulsion systems. So specifically, we're working on the development of hydrogen fuel cell technology to provide electric propulsion to propeller-driven aircraft.
So this is a Piper Cherokee. It's from the 1960s, and we took it, stripped everything out of it so we could convert it to a hydrogen-powered aircraft. So everything forward of the cockpit is new. We have our own engine mount, which you can see in this box here, with all of our hydrogen fuel cell electric propulsion system hardware in it.
So I've basically pulled from all of my experiences to get me to the point where I am today. I think it depends on who you talk to, whether or not they see the value in what the space program does. And I think most people do. You know, NASA has done a great job at communicating that itself.
There's still a lot of science to learn up there so we can better understand what's going on here and what we have to do to keep it the way we want it.
Even beyond the technology is the fact that it motivates so many young people. I became an aerospace engineer because of NASA. Many young people around the world see what the space program does, and they become engineers and scientists because of that. So I think that dream, that inspiration, is probably the most important aspect of what the space program does.
In 2016, I started working on a book called Space 2.0, and the idea was, let's look at the next 25 to 30 years in space and all the great things that are going to happen. So I went around and talked to captains of business and entrepreneurs, mostly in the space trade. I talked to international space agencies. I talked to NASA. I talked to Roscosmos. The conversations were just crackling with optimism. New space is here, finally. You know, all those years, the 70s and 80s, we were talking about, oh, the shuttle's going to fly every week and it'll open up space. That didn't happen. Private entrepreneurs are going to start flying rockets. That'll open things up. That didn't happen. So we kind of had, I wouldn't call it a fizzle, I'd call it a stall.
Back in the 90s, there were some people that were very excited about the space industry and where it could go. However, it was a bit too early. The technology, the funding, and the commercialization weren't mature enough to make that happen back in the day.
With the conclusion of the space shuttle program in 2011,
Houston to planet. After serving the world for over 30 years, the space shuttle has come to a final stop.
we didn't have a way to get astronauts up to our space station that we paid a whole lot for anymore. So the pressure was on, and NASA decided, okay, we'll start using these private companies. They own the spaceships, we're just buying rides, and they're fixed price contracts. And that worked okay, but it was continually underfunded on the government side. Now on the private side, we see interest and investment going up and down and up and down and up and down. But it's better than it's ever been before.
Lunar Voyage 1 has the first commercial rover that's ever going to be on another planetary body. The first rover ever at the Lunar South Pole, and the first sale of space resources in human history. So this is a historic mission. This is massive, not only to set the legal and procedural framework to access the resources of space, but to also show commercial companies can go out there and change the way that humanity utilizes space. So this is going to be a really exciting mission.
The commercial aspect of it is really unique. This vehicle is completely put together through commercial interests. And that really shows kind of a new future.
This mission is also very unique because we have not only a commercial rover, which is what Lunar Outpost makes, but a commercial lander that Intuitive Machines makes, and a commercial rocket, which is what SpaceX makes. So for the first time ever, you have end-to-end commercial providers for a spaceflight mission, which is pretty awesome.
So back during the first space race, 'cause we're kind of in a second one, back during the first space race, NASA would design something, take the specs to the private contractors and say, this is how we want it done, make it work. And it worked great. It was just really expensive. So now we have fixed price contracting. So NASA will go to a private vendor, company, entrepreneur, whatever, and say, okay, here's what I need you to accomplish. You know, we got to get a bunch of stuff up to the moon. This is what we need you to do. This isn't how it needs to be built. Doesn't have to look like this. Doesn't have to have this many moving parts. Tell me how much, and then that's it. We will give you that much. If you need more money, you've got to come back and beg for it and validate to me that you really need it and why that's important. The overall idea is, I've got this much money. I want you to do this, make it work.
What we are doing with MAPP is bringing costs to entry down by multiple orders of magnitude and bringing the timelines in which these rovers are made down by multiple orders of magnitude as well. So it's faster, it's cheaper, and it's still reliable. And that's what allows us to be commercially successful in the long run.
The moon is a really great jumping off place for going beyond, both in terms of a resource and also in terms of science.
Nowadays, I would say talking about cities on the moon, it's no longer 100 years in the future.
When the time comes that you want to stay there long term, you have to have a place for humans to live.
Having something on the surface of the moon where humans are living and working for long periods of time is very difficult. So we have a radiation environment which is very hostile, and we have huge temperature swings. What we have discovered in recent years are lava tubes. They are places where volcanic activity has created caves tunneled into the subsurface. The same thing was happening here on Earth. We could, at some point, put human habitats in these caves on the moon. That would allow us to have an environment where the temperature is consistent, where we don't have these huge swings between day and night. It provides an environment which would be protected from the radiation environment outside. Now, it might be that there are lava tubes which are much more accessible.
We're in Lanzarote, which is part of the Canary Islands in Spain. So this is a great place for us to test our technology, to test that we can actually do the things we want to do around lava tubes on the moon, and we can test that here on Earth first.
I've plugged in a 3D camera, which has its LiDAR and RGB, so it's regular color images, and then the LiDAR gives us the depth. And collecting this data and hoping to recreate a three-dimensional lava tube. And so what I'm actually getting on my screen here is, it's called a point cloud. It's process data, where it actually puts together the image of what we're seeing in 3D. This is really interesting because it looks like a lava tube that you would find on the moon.
One of the things that would be interesting in this early era of exploration that we're seeing now would be to look for lava tubes locations which could be realistically visited by and used by humans. And so early robotic missions are our scouts. They go ahead of lunar missions with humans, they explore locations, they create the information about the moon, about the surface, about these locations that we'll be able to use to create the human missions of the future.
To make history, to do extraordinary things, it takes extraordinary effort. You really have to be bold when you pursue these endeavors, and you really have to go the extra mile at everything you do. Everything counts. And that really has helped us to kind of push the speed in which we're commercializing the space economy. And I think part of that is this dedication to push further. Failure is not an option.
Failure is not an option has been the historic motto of human spaceflight. Back during the Apollo missions, for example, you can't lose an astronaut. You can never lose an astronaut. We very much carried that forward. And so you have to be able to accept failure during testing. You have to be able to accept failure early on in the life cycle of the program. But when you have these systems up on the lunar surface, you have to be able to reliably perform for long periods of time, right? There is no other option.
We do everything we can to burn down as much risk as possible through frequent tests and iteration.
Typically, when engineers in the space industry are talking about testing, they're talking about environmental testing. That leaves out a whole really important area of testing that has to do with actual operation.
Testing is critically important, not only for Lunar Voyage 1, but everything we do. Putting ourselves in the best situation to succeed is an absolute must.
There's so many unknown unknowns that there's always something that's going to happen or something that's going to be unexpected. And so every time we test, we're learning.
Well, and that's exactly what happened this morning in the back left over there. It was just our motor power was like very low, like less than 20%. And it takes
the opportunity that something is going to change on mission is almost guaranteed. So we have a responsibility to train the team so that they can handle those dynamic situations. You know, we have an obligation to customers to make sure that they can get the data return that they need from the mission. And so it's our responsibility to meet that even when we depart from the lander and we see that there's boulders here, here, and here.
We are planning for every contingency.
From a technical standpoint, we've mitigated the risk as much as possible. We've done the integration to the lander. All the technical risk that we can mitigate have been retired at this point.
So what's so unique about working on NASA robotic missions is you have to develop very complex systems and they have to do very unusual things like landing on the surface of another planet, which is hard to do, and you have to make it work the first time. So it's very challenging from an engineering perspective.
When you're designing for an environment that no one's been in 50 years, you have to use all the data that you can, right? All the data that's available to you. There have been other countries that have gone recently, including China and India. However, our access to that data is fairly limited over here in the United States. So we have to try to get as much information as we can to build the best product possible. That being said, we partner very closely with NASA and Colorado School of Mines, who have high fidelity, geotechnically accurate regolith. So the soil that's on the lunar surface, they have recreated a simulant that's very close in its properties that allows us to get a much better feel for what it's like interacting with it and driving on it.
When you're designing something for space, that testing gets a lot more complicated because you need to recreate those really intense environments.
The environment on the moon is really quite extreme. There is nothing like it on Earth at all. It's a very, very difficult place to engineer for. So the lunar surface has very, very large temperature variation. So during the peak of the day, you're in direct sunlight, it can become incredibly hot. So what tends to happen then is your equipment will overheat.
Understanding, okay, you've got your rover, but what are the environmental factors? How cold or how hot is the surface? Where is the sun? How, what's the solar energy from that? There's a lot of really interesting design problems.
Getting rid of heat, keeping yourself cool, is a really real problem. The lunar night is incredibly cold and incredibly dark. So you have 2 weeks of darkness and extreme cold. Electronics actually can't survive those temperatures normally. And so surviving the lunar night is a massive problem. It's really the biggest challenge we have for lunar exploration, is surviving the long, dark, cold lunar night.
Good analysis work that has, on our end, that's shown that if we can keep the battery warm enough, then once the solar panels are re-illuminated, once, dawn comes back around, if we can recharge that battery, in theory, a lot of things should turn on.
So engineering a vehicle or mobility that can even survive long enough to do something useful is an enormous challenge.
Now on top of that, you have lunar dust, which is some of the nastiest stuff that we know in the universe. So you have this incoming shower of meteors and micrometeors, comets and everything else slamming into the moon for billions of years. It whacks into the surface, crushes stuff, sends up a plume of dust and a few rock fragments. but that is never touched by water or wind. So it sits there, it's sharp, it's got little sharp edges, it's hard, it's very nasty.
The Apollo astronauts described, for example, that working with this dust was one of the biggest challenges that they had.
But we're not done yet. Because of the UV, the ultraviolet light from the sun, this dust has an electrostatic charge. So if you get out there with a metal rover or a spacesuit, it just goes and sucks right up to it, and it's like coal dust. It almost sticks like glue. So when you've got a machine driving around up there with axles and seals and joints and all that, this dust wants to find its way in.
That lunar regolith is extremely abrasive, tends to build up on radiators and solar arrays, camera lenses, things like that. And so the whole rover had to be designed to be dust tolerant in addition to all of the other environmental extremes it survived.
Also, at the same time, getting your lubricants right is incredibly important, because if you don't, you're going to have much more rapid degradation, you're going to have much less reliability, and you're not going to be able to operate in those temperature extremes.
There are materials here on Earth that act as a lubricant that when you put them in the space environment actually become the opposite. They become an abrasive. So the material science and the chemistry of the lubrication technologies that we have available to us is absolutely critical for mission success.
So having Castrol as a partner, having those lubricants that can survive and operate in those extreme environments is very important to us and very important to our vision. Castrol has a pretty deep heritage in space, right? This is not Castrol's first rodeo.
We've been active in space for over 60 years, so we've got plenty of experience that we can bring to this collaboration. So yeah, we believe that taking what we've learned from the last 60 years with the Apollo missions, with Space Shuttle, with the International Space Station, the 3 Mars rovers that we've been involved with NASA, we've clearly learned a lot from that.
The ability to withstand radiation, for the lubrication to be where it is needed, to stay on the parts that require lubrication, and to avoid off-gassing. It's really important for spaceflight lubricants to have a low vapor pressure so that they don't evaporate and off-gas and become a coating on other sensitive areas of the rover, like camera lenses.
With Formula One, we have a mobile analytical laboratory that travels to every single race. And what we do is we take a sample of the lubricant from the Formula One vehicle, and we put it through our analytical equipment at the race and do some analysis to understand, is everything as we expected? A bit like doing a blood sample from a person and doing a health check. We do the same thing with the Formula One vehicle. And the same thing will apply to space.
From the founding moment to now, the technology's evolved a lot. We really took an iterative approach to developing MAPP, well matched for the commercial lunar payload services type landers. These are small landers that NASA decided to commercially procure to bring services to the moon. And not only were they enabled by NASA to bring NASA payloads to the moon, but they could also bring commercial payloads. And so that was kind of our ticket to commercializing a small mobility platform.
A payload customer can come to us and say like, hey, we really want to do X experiment or have X payload, and then we can work with them based on landing sites to make that happen. It's adaptable to wherever a customer needs to be.
For Lunar Voyage 1, we're going to be taking all sorts of collaborators along. We're leveraging Nokia's LTE high bandwidth communications technology for streaming of data, which is going to be pretty awesome.
For Nokia, what we're doing is we're proving out their 4G LTE system on the surface of the moon. The rover itself is kind of like an operator or just a person holding a cell phone. It's kind of a stand-in for that, whereas the lander is like the cell tower. And as we traverse across the surface, we can test the strength of it.
We have partners such as MIT on board that are doing the MIT Astroant. The Astroant from MIT is awesome. Our rover drives off the lander, and almost immediately we drive out of our garage, and then we deploy the garage for the MIT Astroant, and then it drives out of its garage. So it's this pretty groundbreaking robotics technology, 20 grams, smaller than a Matchbox car, and it provides us thermal information of how our radiator is performing on another planetary body. So that's some pretty new, some pretty unique information that we wouldn't be able to otherwise get. So this rover, 10 kilogram class, driving a couple kilometers, testing out those critical technologies, working with our partners, all from our Mission Control Center here in Colorado.
This is the Lunar Outpost Mission Control Center. When you look at a single ground station, you'll notice this communication system that has all of our voice loops. It's a key nexus of communication for us. So you'll see every station has one of those. So the flight director would typically use this console here. It's important to have a good view of all of the other screens so you can see what other mission operators are doing. And then also give a good view of the key critical data up there. Our payload officer would sit here. So this person is in charge of communicating with the payloads that are going to have different activities on board. So this would be, we had direct line to MIT set up to their mission control center so we could communicate on activities and give them status of the mission. Here we had the power and thermal officer in charge of monitoring power and thermal telemetry during the mission. It's a very important role as during transit, those are the two key parameters you're really looking for. As the rover goes from Earth to the moon, you want to make sure that it stays warm in the safe non-operational temperatures, and you want to make sure you're getting power.
To power on off, could you do an updated get power distribution on that? I just want to confirm that that payload shut off properly.
And then this far console over here is the Stargate officer. They're the ones monitoring our connection to the ground station, the ground antennas. They're making sure that the commands are going to the moon. We're getting pings back, so it's a very important job. All right, so this is the pilot. So that's a cool role. The pilot is the one that sends the drive commands.
Pilot, we have begun our 20-minute payload activity window.
They also send other commands to the rover, so they need to really be in tune with rover operations, how to drive it. They do a lot of really intense training, both with our simulator and then our Earth model, to get used to what it's like to see from the rover's perspective.
Mission control is the central part of everything from operating rovers in space to bringing in our team, the scientists, the stakeholders here on Earth, and having a place to engage as part of a mission.
Having Castrol as a collaborator on our Mission Control Center, really helped show that now is the time. There's a lot of big international companies and organizations that are ready to operate and do cool new things in space, and they're supporting it. They're ready to go. We're building things. We're launching missions. It's all right here, and it's physical. It's something you can see and touch and interact with and work inside of.
It's great to be involved with another. We've been involved with many kind of world firsts, and this is going to be one of those out of the world firsts, which is tremendous.
I don't think robots are going to take over from astronauts completely, because humans are great at a few things that are just innately human.
We're just faster. We're more facile, our hands are more flexible, we can think on the spot, we can make abstract reasoned conclusions.
What robots will take over are the dull, dangerous, dirty jobs, right? Robots are going to build your infrastructure. Robots are going to maintain your habitats.
We still need to send people to these places. So what other kind of mobility system might we be looking at?
So when we start talking about our space truck, our lunar terrain vehicle, that's a vehicle that has to operate over 15 years on the lunar surface without any maintenance or repair.
The Eagle LTV it's a platform, it's a backbone for mobility and infrastructure in the future.
So the reality in our manufacturing process, we start off in digital design, as a lot of people do nowadays, right? We'll put things in virtual reality, we'll put things in a simulated environment to get a sense of size, scale, and space from a mechanical side. From the software side, we'll do a lot of testing, a lot of simulation for different sensors, different setups, different autonomy algorithms. And once we feel relatively comfortable in the digital space, then we start bringing it into the hardware space. Yeah, so this is Hawk 1.0. So very similar to automotive, how they do clay modeling. We do very quick and dirty modeling in 80/20 in wood to give us a sense of the form, fit, and function of the vehicle. And that allows us to iterate on the design fairly quickly. So everything from how you get in and out of the vehicle, whether there's one step or two step, what that step height is, to how these workbenches actually work and do people use them. And what you can see is like, people are using them. They're using them for non-testing purposes. So that was obviously a hit. So Hawk 1.0, a lot of it's instinct. Once we are done with the quick prototyping, then we head over to the high fidelity metal, it actually starts looking like the real vehicle, and that's the next static mock-up. The difference between our low fidelity and high fidelity mock-ups, high fidelity mock-ups will actually do human factors testing. We'll bring in astronauts that worked on the International Space Station to test out with our vehicle. We'll get team dynamics. We'll have more functional features. So we'll have things like deployable solar panels, functioning lights. If there's steps that need to function, we'll have deployable steps, displays and controls. So it takes it from that concept, that kind of form, if you will, and it puts it into something that is functional from a human perspective. And then we're going to be going through multiple iterations of getting feedback from NASA, making improvements, and then getting more towards that final vehicle design.
The gravity on the moon is about 1/6 as strong as the gravity on the Earth. So that's your downforce. But if you're taking a turn, like you're driving your vehicle and you're turning at a certain speed, you're going to still have the same lateral acceleration for the same speed. But what you don't have is the same downforce. So things on the moon almost feel tippier. So we definitely emphasize things like a low center of gravity. We also have lots and lots of travel in our wheels that help us like float over the surface, because it's a true off-road environment on the moon. There's no roads there, at least yet.
We see this as the core backbone of the Artemis campaign that will actually enable humanity to build outposts and cities on other planetary bodies. This is what makes it possible. Putting humans back on the moon, we could not be more excited, and having that ability to do so commercially is just an opportunity of a lifetime.
MAPP is going to be the first, not only the first privately owned rover to the moon, but the first teleoperated rover manufactured by the United States. The flight rover, yep, it's already been delivered, and we just recently integrated it into the lander hardware. So that rover is ready to go, and that's why you don't see it here today.
It's hard after so many years, not to feel a connection to this little machine that you've put through its paces and gotten it ready to fly, and that you'll never touch or see again.
NASA's had a great success record over the last 6 or 7 decades, and during their time, the Soviet Union had a very high rate of success. And in both cases, I think this made it look a little too easy.
The truth of the matter is what we're doing is not easy. It's not like a movie where we know how it's going to end. The risks are there. There's a lot of risks.
Yeah, it feels like it's been a lot of work.
It's exciting, slightly anxiety-inducing.
The kind of first reality is we have to get there.
Millions of things have to go right for this to get off the ground. So there's the hardware side. There's the interfacing that hardware with the launch pad side. Fuel tanks that have to feed from the ground up into the machine. Well, one of those fuels is hydrogen. Hydrogen's the smallest molecule there is, and it's very leaky. So you have the slightest imperfection in the seal fueling that, and you got to shut down the launch.
They'll make the decision at that point whether to fuel. So if at that point we don't have a go for fueling, then there's a good chance we're not going tonight.
Lunar Voyage 1, launching on a SpaceX Falcon 9, landing on an Intuitive Machines Nova Sea lander. It's always going to be a challenge anytime you're launching something into space.
All we see from the public side is, oh, look, another launch. The guy gave the countdown, 10, 9, 8, 7, 6, and off it goes. It's like one atom at the top of the iceberg in terms of how complicated this all is.
As we worked up to it, I went in the clean rooms, performed the final checkouts, pulled the remove before flight plug, on the rover, and then it was sealed up, and no human was ever going to touch it again.
So let's say those million things do go right, and it's that moment right before launch. Okay, now you're leaving the ground.
You experience launch vehicle vibrations, which result in a lot of loading, sometimes from 10 to 15 G.
Now you're flying.
Shock loading as a result of different pyrotechnic devices going on and off, and then also separation events between the different stages, that everything which is sitting inside of the launch vehicle fairing has to be able to take and accommodate.
There's an awful lot of things that could go wrong, and they're all trying to channel these terrifically huge mechanical forces that are required to get anything of any size off the Earth.
If you can survive launch and connect on orbit, for most space missions, that's a success. You've done well.
It's a reminder of just how incredibly intricate and complex this dance is between people, machinery, and the forces of nature. You can't mess with physics, you know? Physics is physics.
Again, the flame will be a bright orange. It will light up the sky completely.
See and hear it. We're in startup. Everything looks
The space industry is truly amazing. It was a huge moment at launch. We finally got the chance to see our rover, MAPP, head out into space and on its way to the moon.
I think definitely it hits you. I remember being at launch, watching the launch obviously is very emotional, and it was my first rocket launch ever that I was there in person for, and you feel the sound wave hit you and it's like, whoa.
Yeah, I mean, launch events are super exciting. For me, I get a little bit nervous because it's one thing that I don't have a lot of control over, right? The job of the rocket and getting into space is not for us. Our job starts when power is applied to the vehicle during transit, and then we get the first data back monitoring the systems.
We had a remote mission operations center essentially at Kennedy Space Center.
Because our flights were all the next morning, we always had people back here at the Mission Control Center monitoring from here.
Talking to Intuitive Machines over the line, talking about, okay, we're gonna send the power line to turn on MAPP to start getting health signals and telemetry back.
Did it survive launch? Which is one of the most difficult things to do in your path to spaceflight. And so we're sitting there, don't see any pings. We're like, are we gonna communicate? Did they go well? Did we survive launch? Are we healthy?
It was almost as if, my dog was on board there. I felt worried for it.
I'll never forget the time was 1820 Mountain Time when we received the first ping from MAPP, and it's like, oh my God, the rover's alive. I don't know, that was just so amazing.
All right, we survived launch. Now 100,000 kilometers to go. All right.
Everything was exactly as we expected to be. All systems were nominal and happy, and MAPP was ready to fly and transit out to the moon. It was a moment that I'll never forget. The thing that we had spent all these years building and testing was finally on its way and finally in space and alive and doing well.
It's a really difficult environment to build through, and so I think it was important to be grateful for every little thing that goes well, and it's like, wow, we did this as a team, we came together, we built this rover, and it's working so well, and that's just really special.
This was truly a special moment because it showed that everything we had done, all the hard work, all the nights and weekends, all the sacrifices our team had made, had paid off and will pay off massively in the future. And this was the hardest step.
I remember we were driving back from the launch site. We were monitoring the vehicle health and data on our laptop through the Stargate system as we transitioned to the next Mission Control Center that we had set up at the hotel. And then finally, a day later, we were all back here.
And then it's, all right, now we're on our way to the moon.
Heads down, time to focus.
There's still this little bit. The tough work is, left to go. We've got to operate this vehicle through some of the most, dangerous environments, going through radiation belts, going through, landing.
Obviously, we were operating 24/7 actually during transit, which is a really cool opportunity. We were working with 3 or 4 shifts of teams coming in, briefing each other, and then continuing the work.
From Earth orbit out to lunar space in our transit phase, we're facing dark deep space at almost absolute zero.
Flight director thermal, we had component temperature starting to cool off here.
When the lander rotates and now we're in full sunlight, the rover needs to be able to withstand those temperature shifts in a relatively short amount of time.
Negative 200 degrees to positive 150 degrees Celsius.
Our team got honed very quickly, right? Making sure we're solving the issues, the problems, any interaction issues that pop up with the lander. We solved those, we got through it, and our rover behaved perfectly. That 1 week was intense.
Then we enter low lunar orbit as we circularize around the moon. That was interesting because the temperatures got a little bit warmer. The moon itself holds some heat, and so that tended to increase those really low temperatures that we saw during transit. A lot of radiation and, of course, the low pressures of space.
Our rover is now in lunar orbit, which is a massive achievement in and of itself.
Spacecraft power, 14 watts. All systems look nominal.
So all that to say, we're getting close to the moon. Tensions are building. Excitement is building. Our team is getting ready for operations. And we had just been through a week of barely sleeping, everyone's getting ready, everyone's nervous.
So the lander will, make an orbit, get a little closer, and it's sort of a safety thing to get some information about where we're gonna land, what it looks like, to do a lot of that planning and mapping. And then we get closer and closer, and it's sort of, once it's ready, then it goes for the final landing situation.
Another rocket engine firing as the lander came in and prepared to touch down softly on the surface. So
the lander then approaches its landing location sort of sideways like this, and then it turned down so it can land down on its feet.
The lander starts coming down, starts approaching the surface of the moon. And so we flick on the left screen. We flick on the live stream from Intuitive Machines, their public live stream. Right screen, we have our private live stream.
We knew what we expected to see on the screen and to hear from our lander provider.
And we're sitting there and I hope this goes well, because there's not a lot we can do if it doesn't. The live stream kind of goes quiet. Our private communication channel goes quiet. And then we get a call. We get a call that tells us we're not going to be able to deploy on the surface of the moon. And that, it's devastating, right? It's not an easy thing to absorb while you're in the Mission Control Center.
We began to understand that something wasn't quite right about how the lander had landed.
Yeah, so once the lander landed, unfortunately it happened where it essentially tilted itself sideways and ended up sort of crashing into a crater.
It turns out that the weight of the lander was actually on top of the rover, and that wasn't an orientation we were able to exit from.
We do know, though, from our thermal information that it did survive the landing, which is really cool that, survive a crash landing on the moon and to be able to survive in a really cold, possibly permanently shattered region of the moon.
When we discovered that there was an off-nominal landing, it was kind of like our Apollo 13 moment. What can we do with what we have to figure out how to get off this vehicle and continue the mission? So we gathered our resources. We had our team go down to our lunar rover testbed. We built the entire garage to represent where the lander was. That was just an amazing moment of the team coming together to see what we could do to keep going on the mission.
I really wanted to see that first photo from MAPP as it touched down on the lunar surface. So, we always knew that was a possibility, but to stand there in the room and see it happen, it was disappointing.
Our team's better for it, honed through fire, and now is ready for the next challenge.
It's probably one of the most historic milestones in the story of surface mobility. And you may say, hey, does it make sense? Because ultimately the vehicle was entrapped under the lander and didn't drive on the lunar surface. But the number of systems that we demonstrated, the full end-to-end operation of the rover through mission control systems, the full checkout of the vehicle, those things are 99.9% of the challenge for building one of these machines, which is probably one of the most complex machines humankind has made.
Also, we got to validate a number of technologies that we invented for the MAPP mission. Things like the system that holds the rover tightly and protects it during the vibrations of launch and landing. That's our Talon rover hold down system. At the same time, there was also a real sense of pride because MAPP performed flawlessly from launch all the way through transit, lunar orbit, and even that rough landing, which was outside the bounds of what it was designed to survive. So I think I'm really proud, and my whole team is really proud of just how well MAPP worked. It was ready to drive and ready to do a fantastic mission. So as we look towards the future, we know we're ready for what comes next.
I remember the comment when I gathered the entire team in the back of the garage and told them we're not going to be able to drive off, and we're just going to try to get as much data down over the next 8 to 10 hours as possible, however much battery the lander had. And then the first comment that I heard when I was coming back in, let's get after the next mission. There was no downtime, there was no sulking. I mean, don't get me wrong, we're all heartbroken because we can't accomplish 100% of what we set out to do. It brought all of us a little bit closer, and it gave all of us a common shared purpose. We haven't had truly a flagship mobility system on the lunar surface since the lunar roving vehicle. Fast forward to 2029 through 2031, basically those first Artemis missions. Now we're going to have permanent infrastructure for the first time ever on another planetary body, and these are flagship missions. I mean, these are astronauts driving trucks on the moon. So the lunar terrain vehicle, that's going to enable multiple humans to be on the lunar surface around the clock, which is an amazing place to be. This is something that NASA's been thinking about for a while. And when astronauts aren't there, the lunar terrain vehicle has to set up large-scale infrastructure. So this is the single most complicated vehicle and most advanced vehicle, and has to be the most safe and reliable vehicle humanity's ever put on another planetary body. 2022, the lunar terrain vehicle proposal drops. This was services being procured on the moon by NASA. And what that means is NASA believes there's a commercial market, a commercial customer base that can help offset costs to NASA while increasing the value and keeping the safety and reliability that NASA is world-renowned for. We say this is the opportunity of a lifetime. We have to do this. And we ended up with truly, I think, the best team, just a tier 1 world-class team that we're working with. So General Motors, they helped make the original lunar roving vehicle. Goodyear, they made tires as part of the Apollo program. MDA Space, they make all of the robotic arms for the International Space Station, that giant robotic arm. It's even on the Canadian money if you ever actually look at it. Leidos came in at the last minute, and they came in with the human health and performance and the manufacturing capabilities. So for us, having 4 multi-billion-dollar, like all Fortune 500 companies working with us on our team was just a dream come true, but also a daunting challenge. So we put this proposal in, and we had no idea if we won. Absolutely no idea. And we get a call, highest pressure call of your life, right? Like, this is a multi-billion-dollar program. It's either a yes or a no, and that's a pretty big binary. Yeah, we called to tell you today you're a part of the competitive range. We were one of the 3 down selects, and now they needed to make sure they vetted us, go through the contractual requirements, make sure we met it. But if we got through all that, we've won. It was just elation, right? Again, the highest intensity moment, other than trying to actually land on the moon, I've ever had in my life. And that is something that we're still competing on, right? We've just gotten through the phase 1 of our Lunar Terrain Vehicle Services program, and now we're gonna be putting in our proposal for phase 2, and now we're gonna have to wait again. We're gonna have to wait another 4 to 6 months before we get that call. And that call will probably be one of the most 3 stressful moments in my life. Unbelievable experience to get awarded the phase 1, and we hope they give us that opportunity and that responsibility to take humanity back to the moon in phase 2. What keeps me motivated, what keeps me excited is that generational impact that we can have, that long-term impact that we can have for humanity and for people back here on Earth.
You know, I like looking to the next generation as well. I think if we establish a strong baseline of what our capabilities are in space, they can dream even bigger and probably imagine things that, you know, we've never even come up with that they want to do in their generations in space.
I think we are right at the beginning of our journey. The moon it's the next place that we as a species can go.
In a decade, we will have hundreds of rovers. In 2 decades, it'll be thousands. These are the workforce of the lunar future.
I think that this is a wonderful time to be involved because it's the beginning. And the things that we do now and the decisions that we make about how we do this will shape things into the future in ways that I don't think we can even begin to imagine.
There's an old saying, if you want to go far, go together. And that's something that we have taken very seriously.
Exploration is built on international collaboration. Working together is incredibly rewarding. And from a scientific perspective, there are things we can do together that none of us can do on our own. There are things that we can achieve that would be impossible if any one agency or any one organization was trying to do it on their own.
There's brilliance everywhere. The question is, how do you channel it? I think that's the key of the moon becoming this place of opportunity.
There are challenges, but when we get there, when we see something that we have built on the surface of the moon, that will be something really quite extraordinary, that is really unique in the world and is really very special.